Look up at the night sky, and what do you see? A vast, endless ocean of twinkling lights, each one a story waiting to be told. Humanity has always been drawn to the mysteries of space. Our ancestors mapped the stars, named constellations after gods and heroes, and dreamed of touching the heavens. That same awe still burns in us today, but now we're not just dreaming. We're exploring, discovering, and standing on the brink of revelations that could rewrite everything we know about our place in the cosmos. Imagine a single moment in space, a discovery, a collision, a signal from the void rippling through time to alter the course of human history. It's not science fiction. It's a reality we're hurtling toward, one groundbreaking event at a time. What if I told you there are 30 pivotal space events, some looming on the horizon, others already unfolding, that could reshape our future in ways we can barely fathom? These aren't just milestones in science, they're turning points that could redefine technology, transform societies, and even challenge our understanding of life itself. Picture this, a rogue asteroid veering perilously close to Earth, forcing nations to unite in defense. A distant exoplanet revealing signs of life, answering the age-old question, are we alone? Or a breakthrough in propulsion technology flinging open the doors to interstellar travel, turning the stars from distant dots into destinations. Each of these events carries the weight of possibility, the spark of revolution, and the power to change humanity's trajectory forever. This is more than a countdown or a list of facts. It's a journey through the moments that could define our species for centuries to come. We'll explore how a single discovery on Mars might upheave our economies, how a burst of cosmic radiation could wipe out our satellites in an instant, and how the search for dark matter might unlock secrets older than time itself. The universe is unpredictable, and that's what makes it thrilling. So buckle up. By the end of this, you won't just see the night sky as a backdrop. You'll see it as a living, breathing frontier, pulsing with events that could, at any moment, change everything. The question isn't if these events will happen, it's whether we'll be ready when they do. The story of everything, ourselves included, begins with a single, unimaginable moment. 13.8 billion years ago, an unfathomable explosion of energy erupted from a singularity smaller than an atom, sending the entire universe hurtling into existence. This wasn't just the birth of stars or planets, it was the origin of time, space, and every law of physics we now take for granted. In less than a second, the cosmos expanded faster than light itself, a phenomenon called cosmic inflation, stretching the fabric of reality into the vast emptiness we now call home. Yet the Big Bang wasn't some fiery blast in empty space because space didn't exist yet. Instead, it was the creation of space itself, unfolding like an endless cosmic canvas. Within those first critical moments, the simplest particles fused into hydrogen and helium, the building blocks of every galaxy to come. But here's the twist, we still don't fully understand what sparked it. Was it a natural collapse of higher dimensional space, a collision of unseen universes, or something beyond our current comprehension? Even more puzzling is what happened next. As galaxies spun into being, the universe didn't just expand, it accelerated. Some mysterious force, dark energy, pushes everything apart faster and faster, as if the cosmos refuses to sit still. And the wildest part, we can only detect 5% of the universe's total matter. The rest, dark matter, an invisible scaffold holding galaxies together, and dark energy, that enigmatic force stretching the void. Think of it like this, if the universe were a symphony, the Big Bang was the first deafening chord, but we're still hearing echoes of it today. The afterglow of that explosion lingers as cosmic microwave background radiation, a faint whisper of heat from the dawn of time. And buried in that static are clues, hints of how galaxies formed, why matter won over antimatter, and whether other universes might exist beyond our own. This event didn't just shape the cosmos, it made life possible. Every atom in your body was forged in those early chaotic moments, scattered across space until gravity pulled them into stars, planets, and eventually you. Without that initial cataclysm, there would be no Earth, no sun, no ingredients for life. The Big Bang isn't just history, it's the reason we're here to ponder it. And as scientists peer deeper into those first moments, we edge closer to answering the ultimate question: why is there something rather than nothing? The stage was set, a swirling, turbulent cloud of gas and dust drifting through the Milky Way, leftovers from generations of long-dead stars. Then something extraordinary happened. About 4.6 billion years ago, a nearby supernova sent a shockwave rippling through this cosmic cloud, triggering its collapse. Gravity took over, pulling everything inward until the center grew so dense and hot that it ignited. Our sun was born. But the real drama was unfolding in the disk of material circling this newborn star, where countless fragments began clumping together in a violent celestial dance. This wasn't a gentle process. Imagine trillions of asteroids, each no bigger than a pebble, smashing into one another at terrifying speeds. Over millions of years, these collisions built mountains, then moons, then entire worlds. Scientists call this the nebula hypothesis, the idea that our solar system formed from this spinning disk of debris. But here's what's fascinating: not all planets had the same fate. Close to the Sun, only rocky materials could withstand the heat, giving rise to Mercury, Venus, Earth, and Mars. Meanwhile, farther out, gas giants like Jupiter ballooned to enormous sizes, hoarding lighter elements like hydrogen and helium. Jupiter, however, wasn't just a passive giant. It became Earth's silent guardian. With its immense gravity, it acted like a cosmic vacuum cleaner, pulling in rogue comets and asteroids that might have otherwise slammed into our planet. Some scientists even argue that without Jupiter's protection, Earth would have faced so many catastrophic impacts that life might never have gotten a foothold. But Jupiter wasn't the only factor. Earth's position was just right. Nestled in the so-called Goldilocks zone, our planet was neither too close to the Sun to boil away its water nor too far to freeze it solid. And then came the final piece of the puzzle, a Mars-sized object named Theia, crashing into early Earth in a collision so violent it vaporized rock and sent debris hurtling into space. That debris eventually coalesced into our moon, which stabilized Earth's tilt and gave us predictable seasons. Without this cosmic accident, our planet might have wobbled chaotically, making complex life nearly impossible. So when you look up at the night sky, remember, you're not just seeing stars. You're seeing the fragile, almost miraculous chain of events that made your existence possible. The solar system didn't just form, it was forged in chaos, shaped by catastrophe and fine-tuned by chance. And somewhere in that perfect storm of collisions and coincidences, Earth became the oasis it is today. 4.5 billion years ago, Earth wasn't the blue marble we know today. It was a scorching, half-formed world still cooling from its violent birth. Then catastrophe struck. A rogue planet the size of Mars, now called Theia, came barreling through space on a collision course with our young planet. When they crashed, the impact was so apocalyptic it would have vaporized continents instantly. Molten rock sprayed into orbit like a cosmic fountain, while shockwaves reverberated through the solar system. This wasn't just another asteroid strike. It was a planetary demolition that reshaped Earth's destiny. Computer simulations show Theia likely side-swiped our planet at a 45-degree angle, blasting enough material into space to form a seething ring of debris. Within decades, gravity gathered these glowing fragments into what would become our moon. But the evidence isn't just in simulations, it's in the rocks astronauts brought back from lunar missions. Moon samples contain isotopes nearly identical to Earth's mantle, like a chemical fingerprint proving they share the same origin. Yet there's a twist. The moon has far less iron than Earth's core, suggesting Theia's metallic heart sank into our planet during impact, fusing with our own. The aftermath of this collision gave Earth gifts no other planet in our solar system enjoys. When Theia hit, it knocked Earth's axis to a 23.5-degree tilt, the perfect angle to create stable seasons. Without that tilt, we'd have no spring blossoms, no summer harvests, no winter snows. Earth might have wobbled wildly like Mars, where the axial tilt swings chaotically between 0 and 60 degrees over millennia, making climate stability impossible. But the Moon did more than steady our seasons. It became Earth's silent architect. Its gravitational pull slows our planet's rotation, stretching what were originally 4-hour days into the 24-hour rhythm life evolved to follow. Early Earth spun so fast that winds howled at hurricane speeds non-stop. Without the Moon's braking effect, our atmosphere might never have calmed enough for life to take hold. Even tides driven by lunar gravity played a crucial role. Scientists speculate that the constant flushing of coastal areas may have helped concentrate the chemical building blocks of life in shallow pools. Perhaps most astonishing is how rare this event was. Of all the rocky planets, only Earth has such a large, stabilizing moon. Mercury and Venus have none. Mars has only 2 tiny captured asteroids as moons, insignificant compared to our lunar companion. This cosmic accident, violent as it was, might have been the universe's way of tipping the scales in favor of life. Without that cataclysmic crash, Earth could have been just another barren rock. No seasons, no tides, no rhythm to nurture evolution. Theia's collision wasn't destruction, it was the unlikely beginning of everything we know. Just when Earth was beginning to settle from its violent formation, the solar system unleashed one final fury, a relentless storm of asteroids and comets that would define our planet's future. Between 4.1 and 3.8 billion years ago, gravitational disturbances from migrating gas giants sent waves of debris hurtling toward the inner solar system. This period, known as the Late Heavy Bombardment, saw Earth pummeled by impacts so frequent they turned the surface into a molten hellscape, some craters stretching over 1,000 kilometers wide. But this wasn't just destruction. Each impactor carried hidden gifts: water, ice, and organic compounds locked in their cores. When these cosmic bullets struck, they vaporized on impact, releasing torrents of steam that condensed into Earth's first oceans. Scientists estimate that up to half of our planet's water may have arrived this way, delivered by a celestial supply chain of icy comets and water-rich asteroids. Even more astonishing, some of these space rocks contained amino acids, the very building blocks of life. In one famous example, the Murchison meteorite that fell in Australia in 1969 was found packed with over 90 different amino acids, proving that the ingredients for biology can survive the harshness of space. The bombardment may have also created life's first laboratories. Hydrothermal vents at the bottom of newly formed oceans, heated by impact-driven volcanic activity, could have served as natural chemistry sets. Here, mineral-rich waters mixed with organic compounds from space, potentially sparking the reactions that led to self-replicating molecules. Some researchers even suggest that without the constant churning and energy from impacts, Earth might have remained a sterile world. Yet this period was also brutally contradictory. While it may have planted life seeds, it also repeatedly sterilized the planet's surface. The largest impacts would have boiled away entire oceans, with steam atmospheres taking millennia to cool enough for rain to fall again. Any early life forms would have had to retreat deep underground or into resistant niches, creating an evolutionary pressure cooker where only the hardiest survive. This cycle of destruction and renewal might explain why life took so long to establish itself. Each time it gained a foothold, another impact nearly wiped the slate clean. Today, we see echoes of this epoch in places like Australia's Jack Hills, where zircon crystals over 4 billion years old show signs of liquid water, proof that oceans existed even during the worst of the bombardment. And on the Moon, whose scarred surface preserves this violent era like a cosmic time capsule, The giant basins we call seas are actually impact craters from this period, filled later with lava. The late heavy bombardment wasn't just a catastrophe, it was the universe's way of forging Earth into a world teeming with possibility, where destruction and creation danced in perfect, if violent, balance. For nearly 1,500 years, humanity saw itself at the center of everything literally. The universe, according to ancient scholars like Ptolemy, revolved around Earth in a series of perfect crystalline spheres, with planets tracing dizzying loops called epicycles to explain their strange motions. This geocentric model wasn't just science, it was doctrine, tied to religious and philosophical beliefs about humanity's divine place in creation. Then, in 1543, a dying Polish astronomer named Nicolaus Copernicus shattered that worldview with a single radical idea. The Sun, not Earth, was the center of our cosmic neighborhood. Copernicus's heliocentric model didn't just rearrange the planets, it upended humanity's entire self-image. His calculations revealed that Earth was merely another world orbiting the Sun, spinning on its axis to create day and night. Suddenly, the heavens weren't a celestial stage designed for us. They were a dynamic, impersonal system where our planet played no special role, but publishing this truth was dangerous. Fearing backlash from the church and academic elites, Copernicus delayed releasing his magnum opus on the revolutions of the celestial spheres until the year of his death. Even then, his publisher added a dubious preface claiming it was just a mathematical hypothesis, not reality. The resistance wasn't just philosophical. The heliocentric model defied common sense. If Earth moved, why didn't we feel it? Why didn't the stars appear to shift as we orbited? Copernicus couldn't answer these questions yet, but his math was undeniably elegant. By placing the Sun at the center, he eliminated the need for Ptolemy's clunky epicycles, revealing a simpler, more harmonious cosmic order. This mathematical beauty convinced later giants like Galileo and Kepler, who, armed with telescopes and precise observations, would prove Copernicus right. The real revolution, though, was psychological. Heliocentrism didn't just change astronomy, it began the slow, painful process of dethroning humanity from the center of existence. If Earth wasn't special, what did that mean for our place in the universe? This question gnawed at thinkers for centuries, fueling the scientific revolution and challenging the authority of institutions that relied on old cosmologies. Today, we take it for granted that we orbit an average star in a remote corner of a galaxy, but Copernicus's insight was the first step toward that humbling, liberating truth that the universe doesn't revolve around us, and in that vastness, we are both insignificant and extraordinary for our ability to comprehend it. Galileo Galilei didn't invent the telescope, but he turned it into a revolutionary weapon against the cosmos and the dogma of his time. In late 1609, rumors reached the Italian scientist about a Dutch lens grinder's device that could make distant objects appear close. Within months, Galileo had crafted his own version, grinding the lenses himself to achieve an unprecedented 9 times magnification. But instead of training it on earthly targets like most of his contemporaries, he pointed it upward and saw something no human had witnessed before. His first shocking discovery came when he aimed the telescope at the moon. The prevailing Aristotelian view claimed celestial bodies were perfect, smooth spheres, but Galileo's lenses revealed jagged mountaintops, deep valleys, and rough terrain eerily similar to Earth. This wasn't just a new observation, it was heresy. If the heavens weren't perfect, what else had the ancient philosophers gotten wrong? Then came the night of January 7, 1610, when Galileo turned his gaze toward Jupiter. Beside the gas giant, he spotted 3 tiny stars aligned in a straight line. The next evening, they'd moved not randomly, but in a way that suggested they were orbiting Jupiter itself. A fourth soon appeared, completing what we now call the Galilean moons. This simple observation shattered humanity's geocentric delusions once and for all. Here was concrete proof that not everything revolved around Earth. If Jupiter could have its own celestial entourage, then Earth was just another planet circling the Sun, exactly as Copernicus had theorized. But Galileo's telescope revealed even more cosmic disobedience. When he observed Venus, he noticed it displayed phases like the Moon, sometimes a thin crescent, other times nearly full. This could only happen if Venus orbited the Sun, not Earth. Meanwhile, his studies of sunspots proved even our star bore imperfections, its surface marred by dark, shifting blemishes. The backlash was swift and brutal. Church authorities, clinging to Aristotle's teachings, accused Galileo of undermining scripture. By 1633, he stood trial for heresy, forced to recant his findings under threat of torture. Yet his discoveries couldn't be unseen. Those humble lenses had pulled back the curtain on a universe far stranger and more dynamic than anyone imagined, one where Earth was neither central nor special, just a speck in a much grander dance. Galileo's telescope didn't just magnify distant objects, it expanded the very boundaries of human thought, proving sometimes all it takes to change history is a curious mind and the courage to look. Before Newton, the heavens and earth obeyed different rules, or so humanity believed. Apples fell straight down while planets traced mysterious loops in the sky. No one imagined the same invisible hand guided both, until a reclusive English mathematician had a flash of insight that would bind the cosmos together. In 1687, Isaac Newton published Philosophiae Naturalis Principia Mathematica, revealing a force so universal it governed everything from raindrops to galaxies, gravity. Newton's breakthrough wasn't just about math, it was a radical unification of reality. His law stated that every particle in the universe attracts every other particle with a force proportional to their masses and inversely proportional to the square of the distance between them. Suddenly, the Moon's orbit wasn't magical, it was a falling object forever missing Earth, pulled by the same force that made apples drop. Jupiter's dance with its moons, comets streaking past the Sun, all obeyed this simple, elegant equation. The implications were staggering. For the first time, humans could predict celestial motion with precision. Newton's laws let astronomers calculate Halley's Comet's return in 1758 and explain ocean tides as the Moon's gravitational tug on Earth's waters. But the real revolution lay in the future. Without this understanding, spaceflight would remain impossible. Every rocket launch, satellite orbit, and planetary probe relies on Newton's centuries-old insight. When Apollo astronauts navigated to the Moon, they weren't just using advanced computers, they were riding the coattails of Newton's genius. Yet gravity's simplicity hid deeper mysteries. Newton himself admitted he couldn't explain why it worked, only how. This gap would later haunt Einstein, leading to relativity. But for its time, Newton's law was a beacon in the dark, proving the universe wasn't chaotic or capricious. It was a clockwork masterpiece, ticking to mathematical rhythms we could decipher. That revelation didn't just change science, it gave humanity the confidence to reach beyond our world, armed with the certainty that the stars, too, obeyed rules we could master. Einstein's mind bent the universe before anyone else even knew it could flex. In 1915, while World War I raged across Europe, he unveiled a theory so radical it rewrote gravity itself, not as a force, but as the warping of spacetime. Imagine placing a bowling ball on a trampoline. The way it creates a dent that makes nearby marbles spiral inward is how stars and planets bend the fabric of reality around them. This was general relativity, a concept so profound even physicists struggled to grasp it at first. But Einstein's equations did more than explain gravity, they predicted the impossible. Light, he claimed, should curve around massive objects. In 1919, during a solar eclipse, astronomer Arthur Eddington proved it. Stars near the Sun's edge appeared slightly out of place, their light bent by our star's gravity, exactly as Einstein had calculated. Overnight, Newton's straight-line universe became obsolete, replaced by a cosmic landscape where space and time twisted like taffy. Then came the strangest prediction of all: black holes. Einstein's math suggested that if enough mass crammed into a tiny space, it could puncture space-time, creating a bottomless pit from which not even light could escape. For decades, these were considered mathematical curiosities until 1971, when astronomers detected Cygnus X1, a cosmic vacuum cleaner devouring a nearby star. Today, we've photographed the shadow of a supermassive black hole at the heart of galaxy Messier 87, its event horizon a perfect confirmation of Einstein's nightmare. Yet relativity isn't just about faraway monsters. It's in your pocket right now. GPS satellites orbit high enough that they experience time slightly faster than clocks on Earth, a relativistic effect that would throw off navigation by kilometers per day if uncorrected. Engineers must account for this time warp, tweaking satellite clocks to sync with ours. Without Einstein's insight, your ride-share app would guide you into a lake. The true genius of general relativity lies in its universality. From the Big Bang's birth pangs to the orbits of pulsars, from gravitational waves rippling through space-time to the expansion of the cosmos itself, every major discovery in modern cosmology traces back to those 1915 equations. Einstein didn't just give us a new theory of gravity. He handed us the keys to understanding the universe's grandest machinations, proving reality is far wilder than anyone had dared to dream. October 4, 1957, a metal sphere no bigger than a beach ball streaked across the pre-dawn sky over Kazakhstan, emitting a radio signal so simple it could be picked up by amateur operators worldwide. This was Sputnik 1, humanity's first artificial satellite, and its unassuming beep sent shockwaves far beyond Earth's atmosphere. To the average listener, it might have sounded like static. But to Cold War superpowers, it was a klaxon blaring the start of a new era. The Soviet Union's success struck like a thunderbolt. Sputnik weighed just 83 kilograms, yet its psychological impact dwarfed any weapon. For the first time, an object crafted by human hands orbited independently above Earth, completing a full circuit every 96 minutes. American newspapers blared headlines like "Red Moon over US," while citizens gathered in backyards, straining to glimpse the tiny, sun-reflecting dot racing overhead. But the real panic brewed in Washington. If the USSR could launch satellites, they could theoretically loft nuclear warheads across continents, rendering oceans obsolete as defenses. Overnight, space transformed from a scientific frontier into a geopolitical battleground. The United States rushed its own satellite program, only to suffer humiliation when the Vanguard rocket exploded on live television in December 1957, earning the nickname Captivated. Meanwhile, Soviet Premier Nikita Khrushchev weaponized Sputnik's success, boasting, "The United States sleeps under a Soviet moon." The message was clear: communism had outmaneuvered capitalism in the ultimate high ground struggle. Yet Sputnik's legacy wasn't just fear, it catalyzed unprecedented investment. Within months, the U.S. established NASA and passed the National Defense Education Act, funneling billions into science and engineering. The space race had begun in earnest, culminating in Kennedy's vow to land on the moon. But perhaps Sputnik's quietest revolution was in democratizing space itself. Its radio transmitter operated on frequencies accessible to civilian ham radios, inviting ordinary people to participate in this new age. Schools hosted moonwatch clubs tracking satellites with homemade equipment. The heavens were no longer the exclusive domain of astronomers, they'd become a shared human arena. Looking back, Sputnik's true breakthrough wasn't technological. It exposed how fragile earthly power structures seem when viewed from orbit. That humble beep didn't just announce a satellite's presence, it echoed humanity's first step toward becoming a multiplanetary species. April 12, 1961, a single word, poikoli, let's go, crackled over the radio as a 27-year-old Soviet cosmonaut named Yuri Gagarin hurtled into the heavens atop a modified nuclear missile. For 108 minutes, the Vostok 1 capsule carried him around Earth at 28,000 kilometers per hour, completing a single orbit that rewrote human history. Strapped inside a sphere barely 2 meters wide, Gagarin saw what no person had witnessed before our planet as a fragile blue marble, suspended in endless black. The geopolitical stakes couldn't have been higher. Just 3.5 years after Sputnik, the Soviets had again outmaneuvered the United States, this time by putting a human in space. Gagarin wasn't merely an astronaut, he was a propaganda icon. His boyish grin and humble peasant background embodied Soviet ideals, proof that communism could triumph where capitalism faltered. Western leaders panicked. If the USSR could launch men into orbit, what else might they commandeer? The space race was no longer about satellites. It had become a battle for human survival. Yet behind the political theater lay staggering risks. Engineers hadn't fully solved the challenges of re-entry. Gagarin's capsule lacked landing thrusters, forcing him to eject 7 kilometers up and parachute down separately. Soviet Premier Nikita Khrushchev lied about this detail for years, fearing the flight wouldn't count as a true space mission if the pilot didn't land inside his craft. Even Gagarin's survival was uncertain. Doctors worried weightlessness might paralyze him or drive him insane. His only controls were locked behind a 3-digit code, accessible only if he proved mentally competent mid-flight. Gagarin's journey ignited imaginations worldwide. From London to Jakarta, crowds poured into streets to celebrate this shared human milestone. Newspapers hailed him as Columbus of the cosmos, while his modest charm, like admitting he packed sausage and bread in case he got hungry, made spaceflight feel achingly human. Behind the scenes, though, his success lit fires under NASA. President Kennedy, desperate to reclaim momentum, would commit to the moon just 6 weeks later, declaring, "If we cannot lead, we cannot win." The cosmic perspective Gagarin brought back was profound. Circling the Earth, I marveled at the beauty of our planet. He later wrote, "People of the world, let us safeguard this beauty, not destroy it." In those brief, weightless minutes, nationalism faded against the backdrop of a borderless world, a vision that still echoes in international space collaboration today. His flight proved humans could survive the void, but more importantly, it revealed how small Earth truly is when seen from above. That shift in perspective, more than any technological feat, may be Gagarin's greatest legacy. July 20th, 1969. The lunar module Eagle hung mere meters above the Sea of Tranquility, its fuel gauge blinking red as alarms screamed through the cabin. Neil Armstrong's heart pounded twice its normal rate as he manually piloted the spacecraft over a boulder-strewn crater, hunting for safe ground with just 30 seconds of fuel left. Then came the words that defined a generation: contact light, engine stop. 400,000 kilometers from home, humans had finally touched another world. This wasn't just a landing, it was a ballet of precision and brinkmanship. Every system in Eagle was a masterpiece of analog ingenuity, from its hand-woven computer core with less processing power than a modern calculator to the ablative heat shield that had to withstand temperatures hot enough to vaporize steel. When Armstrong radioed, "The Eagle has landed," he wasn't just announcing success, he was confirming that thousands of engineers had threaded a needle across the cosmic void, overcoming mathematical margins so thin even NASA called it a controlled crash. Then came those immortal 11 seconds. As Armstrong descended the ladder, a global audience of 600 million watched his bulky boot hover above the gray dust. His slight pause wasn't hesitation, he was ensuring the fragile lunar module wouldn't tip upon his exit. When his foot finally pressed into the regolith, compressing it like powdered charcoal, his words, "That's one small step for man, one giant leap for mankind," were more than poetry. They marked the moment Earth ceased to be humanity's only habitat. But behind the triumph lay surreal details few appreciate. The astronaut spacesuits designed to stop micrometeorites were stitched by Playtex bra engineers using techniques from lingerie manufacturing. The lunar camera, hastily built by Westinghouse, transmitted footage so ghostly that TV networks had to sharpen it by pointing their own cameras at control room monitors. Even the flag planting nearly failed. The lunar soil was so hard Armstrong had to hammer the pole like a tent stake, worrying it might topple live on air. Apollo 11's legacy transcends national pride. That single mission yielded 22 kilograms of moon rocks, revolutionizing planetary science. The passive seismic experiment they left behind revealed moonquakes, proving our satellite wasn't geologically dead. But perhaps its greatest gift was perspective. The iconic Earthrise photos, showing our fragile blue world suspended in darkness, fueled the environmental movement and reshaped how humanity saw itself. In conquering the moon, we didn't just reach outward, we gained the vision to better cherish our only home. Crafted from gold-plated copper and sealed in aluminum casings, 2 phonograph records no larger than dinner plates hurtle through interstellar space at 17 kilometers per second, carrying the essence of humanity to the stars. When NASA launched Voyager 1 and 2 in 1977, their primary mission was planetary exploration, but their most enduring legacy would be these golden records, time capsules designed to outlast Earth itself. Curated by astronomer Carl Sagan and his team, each record's contents were an interstellar Rosetta Stone. Etched onto its surface are diagrams explaining our planet's location using pulsar maps, cosmic lighthouses whose unique frequencies could guide extraterrestrials to Earth. The records also include analog audio, greetings in 55 languages from Akkadian spoken in ancient Mesopotamia to the Welsh Aichyd Da, alongside an hour of encoded images depicting human anatomy, DNA structures, and everyday scenes like a mother nursing her child. But the most haunting track might be the brainwave recording of Androuillan, Sagan's collaborator and later wife, who meditated on the concept of love while her neural activity was converted into sound. The musical selections were a democratic ode to Earth's diversity. While Bach's Brandenburg Concerto represented Western classical traditions, the record also featured Senegal's percussion, Australian Aboriginal didgeridoos, and Chuck Berry's Johnny B. Good, a nod to the then nascent rock revolution. Sagan fought to include the latter despite some academics dismissing it as adolescent noise, arguing that if aliens received the record, they deserved to hear humanity's full creative spectrum. Yet the golden records almost never happened. NASA initially rejected the concept as frivolous until Sagan convinced them that including a message would capture public imagination, which it did. The records became cultural phenomena, inspiring album covers, art installations, and even a Star Trek movie plot. Their contents reflected late 20th century optimism, devoid of references to war, pollution, or poverty, a deliberate choice to showcase humanity's aspirational self rather than its flaws. In 2012, Voyager 1 crossed the heliopause, the boundary where the sun's influence wanes and interstellar space begins. Its instruments detected a 40-fold increase in cosmic rays, proof it had entered the galactic ocean. The records, with their half-life of 1 billion years, now drift through a void so vast they'd need 40,000 years to reach the nearest star. They may never be found. But as Sagan noted, launching them was less about contacting aliens and more about holding a mirror to ourselves. A reminder that for one fleeting moment, our species cast a whisper into the cosmic dark, saying, "We were here." In 1985, a team of British scientists made a chilling discovery over Antarctica, a gaping hole in Earth's ozone layer, so vast it could swallow the entire continent. But this wasn't just another atmospheric anomaly. It was a planetary emergency, and we might never have known about it without eyes in the sky. NASA's Nimbus 7 satellite had been silently collecting data since 1978, revealing a disturbing trend. Each spring, ozone levels over the South Pole plummeted by as much as 70%. The culprit, human-made chlorofluorocarbon CFC, once hailed as miracle chemicals in refrigerators and aerosol cans, now tearing apart the very shield that protects life from the sun's deadly ultraviolet rays. What made this discovery so groundbreaking wasn't just the science, it was how space technology turned a slow-motion crisis into a global wake-up call. Ground stations had noticed ozone declines for years, but without satellites painting the full picture, the data seemed fragmented, even questionable. Nimbus 7's composite images changed everything. They showed the hole as a swirling, continent-sized vortex, undeniable as a fingerprint. Suddenly, the abstract concept of environmental damage had a face, and it was staring back at us from orbit. The response was unprecedented. Within 2 years of the satellite findings, 24 nations signed the Montreal Protocol, agreeing to phase out CFCs entirely. It wasn't just diplomats at the table. Space agencies and atmospheric scientists became unlikely heroes, their data transforming into political currency. Satellites like Europe's Ibris and later NASA Aura would become the world's atmospheric watchdog, monitoring compliance by tracking chlorine levels in real time. Here's what's truly astonishing. This space-driven intervention worked. By 2019, NASA confirmed the ozone hole had shrunk to its smallest size since tracking began, proof that when armed with orbital intelligence, humanity can reverse even its gravest mistakes. The ozone crisis wasn't just an environmental lesson, it was a dress rehearsal for climate change, showing how space technology could turn planetary stewardship into a shared mission. Those satellites did more than observe. They gave us a mirror reflecting both our capacity for harm and our power to heal. April 24, 1990. The Space Shuttle Discovery roared into orbit carrying what would become the most famous telescope in history, Hubble. Named after astronomer Edwin Hubble, who proved galaxies existed beyond our own, this $2.5 billion observatory promised to peer deeper into the cosmos than ever before. But just weeks after deployment, astronomers received their first images, and their stomachs dropped. The pictures were blurry, not slightly out of focus, but catastrophically distorted, as if Hubble were looking through a funhouse mirror. The culprit, a flaw in the telescope's primary mirror, polished painstakingly for years, yet ground 0.002 of a millimeter too flat at the edges. This microscopic error, smaller than a human hair, scattered light across Hubble's instruments instead of focusing it. The media pounced, branding Hubble a national embarrassment. Late-night comedians joked NASA had built the world's most expensive nearsighted telescope. Behind the scenes, engineers scrambled for a solution, knowing Hubble's survival hinged on an unprecedented orbital repair mission. What followed was one of NASA's greatest redemption arcs. In December 1993, astronauts aboard the shuttle Endeavour performed 5 grueling days of spacewalks to install COSTAR, the corrective optics space telescope axial replacement, essentially giving Hubble a pair of glasses. The moment of truth came weeks later when new images streamed in, crisp, staggering clarity. Stars that had been smeared blobs now resolved into pinpoints. Nebulae that looked like foggy stains erupted with intricate detail. Then Hubble delivered its masterpiece. In 1995, astronomers pointed the telescope at a seemingly empty patch of sky near the Orion constellation. Over 10 consecutive days, Hubble gathered photons, each exposure revealing galaxies so distant their light had traveled billions of years to reach us. The resulting image, known as the Hubble Deep Field, showed 3,000 galaxies in a speck of space no larger than a grain of sand held at arm's length. Overnight, it transformed our understanding of the universe's scale and humanity's place within it. But Hubble's most iconic revelation came from closer to home. In 1995, it captured the pillars of creation, towering columns of gas and dust in the Eagle Nebula where new stars were being born. The image, with its ethereal glow and cathedral-like spires, became astronomy's Mona Lisa, gracing textbooks and dorm room posters alike. Later observations showed the pillars had likely already been destroyed by a supernova shockwave, making the photo a cosmic fossil, showing us structures that no longer existed by the time we saw them. Hubble's impact transcends pretty pictures. Its data confirmed the universe's accelerating expansion, proving dark energy's existence. It tracked weather on Pluto and found water plumes on Jupiter's moon Europa. Most importantly, it taught us that even our greatest failures can become triumphs if we have the courage to fix them. Floating 600 kilometers above Earth, this repaired telescope didn't just show us the universe. It showed us what humanity can accomplish when we refuse to surrender to the darkness. For centuries, astronomers wondered if other stars hosted planets, or if our solar system stood alone in the cosmos. Then in 1995, Swiss astronomers Michel Mayor and Didier Queloz dropped a bombshell. They'd found a planet orbiting not our sun, but a distant star called 51 Pegasi. This wasn't just any world, it was a gas giant hugging its star closer than Mercury orbits ours, completing a full circuit in just 4 days. Nicknamed Hot Jupiter, this discovery shattered all expectations. Conventional wisdom had assumed planetary systems would resemble ours, with small rocky worlds near the star and giants farther out. 51 Pegasi b proved the universe loved breaking rules. But the real revolution came in 2009, when NASA launched the Kepler Space Telescope, a cosmic census taker designed to stare unblinkingly at one patch of the Milky Way. Its mission: detect the telltale dimming of stars as planets crossed their faces. Kepler's precision was staggering. It could spot a star's brightness dipping by just 1/100%, like catching a fruit fly passing in front of a car's headlight from miles away. Over 4 years, this unassuming spacecraft catalogued over 2,600 confirmed exoplanets, revealing a menagerie of worlds stranger than any sci-fi writer dreamed. There were diamond planets, molten lava worlds, and super-Earths caught in perpetual twilight, tidally locked to their stars. Then came the Holy Grail, Kepler 452b. Discovered in 2015, this planet became famous as Earth's older cousin, a world just 1.5 times our size, orbiting in its star's habitable zone where liquid water could exist. Its sun, Kepler 452, is eerily similar to ours, same temperature, same spectral class, but 6 billion years older. Imagine a planet with Earth-like conditions that's had 2.5 times longer for life to evolve. The implications are staggering, yet the search for life extends beyond orbital positioning. Astronomers now hunt for biosignatures, chemical fingerprints in exoplanet atmospheres that could betray biological activity. Oxygen, methane in unexpected ratios, or even industrial pollutants like chlorofluorocarbons might hint at alien civilizations. Recent breakthroughs with the James Webb Space Telescope have already detected water vapor and carbon dioxide on distant worlds, teasing the possibility of atmospheric analysis on Earth like exoplanets within our lifetimes. The most humbling lesson from exoplanet research: diversity. Our solar system, once the model for planetary formation, now seems like just one variation in a cosmic symphony. Some stars host planets orbiting backward, others have worlds with 3 suns in their skies. Statistically, there should be more planets than stars in our galaxy, meaning trillions of chances for life to emerge. Every new discovery whispers the same thrilling question: if the universe has already defied our expectations this much, what else might be waiting in the dark? When the twin rovers Spirit and Opportunity bounced onto the Martian surface in January 2004, cushioned by airbags the size of swimming pools, scientists hoped they might last 90 days. No one predicted Opportunity would endure for 15 years, covering 45 kilometers of alien terrain and uncovering proof that Mars once rippled with liquid water. Its most startling find came in Meridiani Planum, where the rover's grinding tool revealed sedimentary layers packed with tiny spherical concretions nicknamed blueberries. These weren't just geological oddities, they were iron-rich minerals that only form in water, like cosmic breadcrumbs leading to an ancient Martian shoreline. Then came Curiosity, rolling into Gale Crater in August 2012 like a robotic geologist on steroids. Armed with a laser that could vaporize rocks from 7 meters away, it hit pay dirt in 2015 when it drilled into mudstone and detected organic molecules, carbon-based compounds essential for life as we know it. This wasn't direct evidence of biology, but it proved Mars had the right ingredients in its pantry. Even more tantalizing were Curiosity's methane readings. On Earth, most methane is produced by living organisms. When Curiosity sniffed sporadic bursts of this gas in the Martian atmosphere, it raised eyebrows worldwide. Could there be microbial Martians exhaling beneath the surface? Perseverance, landing in Jezero Crater in February 2021, took the baton with a daring new mission. Its landing site wasn't chosen randomly. Satellite images showed what looked like a dried-up river delta, complete with sediment layers where water once fanned out into a lake. The rover's first major discovery, igneous rocks altered by water, confirming the area was not just wet but potentially habitable billions of years ago. But Perseverance isn't just exploring, it's packing souvenirs. Using a drill more sophisticated than a Swiss watch, it's sealing pristine rock samples in titanium tubes that future missions will retrieve and bring to Earth. These could be the first pieces of another planet humanity gets to study up close. The rover's cumulative findings paint a transformative picture. Mars wasn't always the frozen desert we see today. It had lakes that shimmered under a thicker atmosphere, rivers carving canyons, and hot springs bubbling with chemistry ripe for life. Every new discovery peels back another layer of the ultimate planetary mystery. If life ever flickered into existence beyond Earth, Mars may hold the answer. These robotic explorers aren't just machines, they're time travelers, reconstructing a world that vanished before multicellular life even began on our planet. And with each transmission from the Red Planet, they rewrite the story of where we might find our cosmic neighbors. After traveling 6.4 billion kilometers over 10 years, the Rosetta spacecraft faced its greatest challenge, delivering a washing machine-sized lander onto a comet tumbling through space at 55,000 kilometers per hour. The target, Comet 67P, a 4.5 billion-year-old cosmic iceberg shaped like a rubber duck, its surface pocked with cliffs taller than the Empire State Building. This wasn't just another robotic landing. It was humanity's first attempt to hitch a ride on a comet, chasing answers to one of our oldest questions. Did these icy wanderers bring water, and perhaps even life's ingredients, to early Earth? Phila's descent on November 12, 2014, played out like a cosmic slapstick routine. Designed to anchor itself with harpoons, the lander instead bounced twice, once soaring a kilometer back into space before finally coming to rest in a shadowy crevice now known as Abydos. Tilted against a boulder with one leg dangling in space, its solar panels starved of sunlight, Phila had mere hours to complete its mission before its batteries died. Yet in that frantic window, its instruments drilled into 67P's crust, analyzing chemistry untouched since the solar system's birth. What they found rewrote textbooks. Mass spectrometers detected organic molecules including glycine, the simplest amino acid used by life on Earth. More startling was the water. Comet 67P's ice bore a distinct chemical fingerprint heavy with deuterium, an isotope rarely found in Earth's oceans. This suggested comets like 67P couldn't have been our planet's primary water source, overturning decades of planetary science dogma. Instead, the data pointed to asteroids as the main delivery system, with comets contributing just a fraction of Earth's wet ingredients. Yet Rosetta's true legacy lies in the unexpected. As 67P neared the Sun, Rosetta witnessed geysers erupting from its surface, jets of gas and dust so powerful they could have lifted the spacecraft clean off the comet. These eruptions contained molecular oxygen, a gas so reactive scientists never expected it to survive from the solar system's infancy. Its presence hints at chemistry far more complex than anyone predicted, locked in ice older than the planets. Philae's bumpy landing and Rosetta's orbital dance revealed something profound: comets aren't just dirty snowballs. They're time capsules preserving the solar system's rawest materials, and their chaotic paths may have peppered countless young worlds with life's building blocks. While 67P didn't solve the mystery of Earth's oceans, it proved one thing unequivocally: the ingredients for life are everywhere, waiting in the cosmic freezer. We just had to catch one to find out. On September 14, 2015, at 5:51 in the morning, a ripple passed through Earth so subtle it stretched the entire planet by less than 1,000th the width of a proton. This wasn't some seismic tremor. It was a gravitational wave, a warp in spacetime itself, generated by a cataclysm 1.3 billion light-years away. When the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected this faint signal, astronomers heard something unprecedented: the death spiral of two black holes, each roughly 30 times the mass of our Sun, merging into one. The waveform sounded like a cosmic chirp when sped up, a fleeting whoop, lasting just 0.2 of a second that confirmed Einstein's century-old prediction about space's ability to stretch and squeeze like taffy. What made this discovery revolutionary wasn't just proving gravitational waves exist, it was opening an entirely new sense for exploring the universe. Until then, astronomy relied entirely on light, visible, radio, X-rays, but gravitational waves let us hear the cosmos. These distortions travel unimpeded through dust, gas, even entire galaxies, carrying information about events too violent or dark to emit light. LIGO twin detectors, separated by 3,000 kilometers in Louisiana and Washington, work like cosmic microphones. Each facility shoots laser beams down 4-kilometer vacuum tubes, measuring how passing gravitational waves minutely alter the beam's travel time. The precision is staggering, comparable to measuring the distance to Alpha Centauri down to the width of a human hair. The collision itself defied imagination. In their final milliseconds, the black holes whirled around each other at half-light speed, converting 3 suns' worth of mass into pure gravitational energy, more power than all the stars in the observable universe combined. This energy radiated outward as waves, warping spacetime like a boat's wake disturbs water, before finally reaching Earth over 1 billion years later. The detection validated not just relativity, but also the existence of stellar mass black hole binaries, a configuration theorists weren't sure even existed in nature. Then came the real game-changer: multi-messenger astronomy. When LIGO and its European counterpart, Virgo, detected 2 neutron stars colliding in August 2017, telescopes worldwide swiveled to catch the aftermath. They witnessed a kilonova, a flash of heavy elements like gold and platinum forged in the cosmic furnace. For the first time, humanity observed an astronomical event through both gravity and light, like seeing lightning and hearing thunder simultaneously. This one event explained the origin of half the periodic table's heaviest elements, while measuring the universe's expansion rate with unprecedented accuracy. Gravitational waves didn't just add to astronomy, they transformed it. Now, when a star explodes or black holes merge, we don't just see the aftermath, we feel the space-time vibrations of the event itself. It's as if the universe, after eons of silence, has finally begun whispering its secrets directly into our detectors. And with every new chirp from the dark, we gain fresh evidence that even the most violent cosmic events leave echoes, ripples in the fabric of reality that tell stories no telescope could ever reveal alone. SpaceX's launch complex stood eerily still on December 21, 2015, as a Falcon 9 rocket roared back from orbit, not as a fireball streaking toward destruction, but as a controlled descent aiming for a perfect upright landing. Flames licked its carbon fiber legs as stabilizing thrusters pulsed, correcting its trajectory in real time like a cosmic ballet dancer. Then came the thunderous touchdown, the first time in history a rocket's first stage returned intact from space. This wasn't just engineering, it was economics rewritten. Prior to SpaceX, orbital rockets were disposable, their multi-million-dollar boosters discarded into the ocean after one use. Falcon 9's reusability slashed launch costs from $65 million per mission to as low as $15 million, a revolution comparable to transforming airplanes into single-flight objects. The secret sauce, SpaceX's relentless trial and error approach. Early attempts ended in fiery explosions, with boosters toppling into the ocean or crashing onto drone ships. But each failure fed improvements, algorithm tweaks for precision landing, titanium grid fins for steering, and a final suicide burn maneuver where engines ignite at the last second to nullify descent speed. By 2018, the spectacle became routine, with Falcon 9 boosters sometimes flying 10 times before retirement. The financial ripple effect was immediate. Competitors scrambled to develop their own reusable systems, while satellite companies that once budgeted for single launches now planned constellations of thousands. Yet SpaceX's ambitions stretch far beyond cost-cutting. The colossal Starship, standing 120 meters tall with stainless steel hulls gleaming like retro sci-fi, represents Elon Musk's gambit to make Mars colonization feasible. Designed for full reusability, both booster and spacecraft, Starship aims to carry 100 tons of cargo or 100 passengers per flight at costs lower than traditional rockets. Its Raptor engines burn methane, a fuel theoretically producible on Mars using subsurface ice and atmospheric carbon dioxide. Test flights have ended in spectacular mid-air detonations, but each explosion refines the design, inching closer to orbital refueling capabilities that could turn Starship into an interplanetary ferry. The privatization of space access has sparked fierce debate. Critics argue SpaceX's dominance risks monopolizing orbital infrastructure, while advocates counter that competition drives innovation, like Blue Origin's New Glenn or Europe's reusable Prometheus engine. What's undeniable is how SpaceX demolished bureaucratic inertia. Where governments moved cautiously, private firms iterated rapidly, embracing risk to achieve what NASA once did in the Apollo era. Now, with lunar lander contracts and Starlink satellites blanketing the globe, SpaceX proves that profit motives and exploration aren't mutually exclusive. The age of disposable rockets is over, replaced by an era where spacecraft return like airplanes, refuel, and fly again, turning sci-fi's wildest dreams into routine spreadsheet calculations. On October 19, 2017, astronomers at the Pan-STARRS telescope in Hawaii spotted something streaking through our solar system that didn't belong. At first glance, it appeared to be a fast-moving asteroid, except its speed and trajectory revealed an impossible truth. This wasn't some local space rock, it was an interstellar intruder, the first ever confirmed visitor from another star system. Named Oumuamua Hawaiian for scout or messenger from afar, this mysterious object defied all expectations from the moment it was detected. Tumbling through space at 87,000 kilometers per hour, Oumuamua's most baffling feature wasn't its origin, it was its shape. Observations suggested an elongated, cigar-like structure, stretching perhaps 800 meters long but only 80 meters wide. No natural object in our solar system looks like that. Even stranger was its movement. As it hurtled away from the sun, Oumuamua accelerated slightly, as if pushed by an unseen force. Comets often exhibit similar behavior when solar heat vaporizes their ices, creating a propulsive jet of gas. But Oumuamua showed no visible coma or tail, the telltale signs of outgassing. This anomaly sparked a firestorm of debate. Harvard astrophysicist Avi Loeb controversially suggested Oumuamua might be artificial, a light sail or derelict probe from an alien civilization using sunlight pressure for propulsion. Mainstream astronomers countered that it could be a rare dark comet, a rocky body with hidden pockets of ice that sublimated without producing visible dust. Others proposed it might be a fragment of a Pluto-like world, sheared off by some distant cosmic collision and hurled into interstellar space. The truth remains elusive. By the time Oumuamua was spotted, it had already passed Earth and was racing toward the outer solar system. Telescopes had only weeks to gather data before it faded from view, leaving critical questions unanswered. Was it a weirdly shaped space rock with peculiar outgassing properties, or something far more extraordinary, a piece of alien technology silently drifting through our cosmic neighborhood? The legacy of Oumuamua isn't just scientific, it's strategic. Its brief visit exposed how unprepared we are to study interstellar objects. In response, projects like the European Space Agency's Comet Interceptor and NASA have planned rapid response missions aimed to catch the next visitor before it slips away. If another Oumuamua appears, we might launch a probe to rendezvous with it, photograph its surface, and finally unravel the mystery. Until then, this enigmatic traveler serves as a tantalizing reminder. The universe is full of surprises, and some of them might already be passing through our backyard. On April 10, 2019, humanity stared into the abyss, and the abyss stared back with a fiery ring of light. The Event Horizon Telescope collaboration unveiled the first ever image of a black hole, capturing the supermassive monster at the heart of galaxy Messier 87, 55 million light-years away. This wasn't just a photograph, it was a monumental triumph of physics, computational wizardry, and international collaboration, proving Einstein's theories under conditions more extreme than any laboratory could simulate. The image revealed a perfect shadow of the black hole's event horizon, the point of no return, encircled by a lopsided halo of superheated plasma spiraling into oblivion at near light speed. That asymmetric glow wasn't a flaw in the image. It was the signature of space-time itself being twisted like taffy by the black hole's rotation. As matter in the accretion disk orbits the void, particles on one side whip toward us, appearing brighter due to relativistic beaming, while those moving away dim into the background. This matched Einstein's equations down to the pixel, showcasing how gravity bends light into a cosmic funhouse mirror. Capturing this image required a telescope as big as Earth itself. The Event Horizon Telescope wasn't a single observatory but a network of 8 radio telescopes spanning from Hawaii to the South Pole, synchronized to function as one global lens. For 5 nights in April 2017, these dishes trained on M87, collecting petabytes of data. So much that physical hard drives had to be shipped to central processing facilities because transmitting it electronically would have taken years. Then came the Herculean task of stitching together the signals, a computational feat akin to reconstructing a symphony from musicians playing on different continents. The image answered lingering questions while sparking new mysteries. The black hole's mass, 6.5 billion suns, matched predictions based on the orbits of surrounding stars, validating decades of indirect measurement techniques. But theorists were stunned by how closely the observed shadow matched simulations of a spinning black hole described by the Kerr metric, Einstein's solution for rotating singularities. Some had expected quantum effects or exotic physics to warp spacetime differently at such extremes, yet relativity held firm even here. Beyond confirming century-old math, this snapshot revolutionized how we study black holes. Before, these cosmic predators were like characters in a radio drama, inferred by their gravitational voices but never seen. Now they're tangible, their features open to scrutiny. Future upgrades adding space-based antennas could sharpen the images enough to track violent flares around our own Milky Way's black hole, Sagittarius a star, or even test whether black holes bounce when they collide. Most profoundly, the image made the abstract viscerally real. For generations, black holes existed only as equations on chalkboards or blurry artists' concepts. Now anyone can point to that glowing ring and say, that's where the fabric of reality breaks. It's a reminder that even the universe's most alien phenomena obey laws we can comprehend, and that humanity's curiosity, armed with enough ingenuity, can illuminate even the darkest corners of creation. What began as a theoretical oddity in Einstein's notes became, a century later, a beacon proving that the universe's most extreme environments are not beyond our understanding, only awaiting the right tools to reveal them. The fiery halo of M87's black hole isn't just light. It's the glow of scientific perseverance piercing the dark. For 60 years, every lunar mission had one thing in common. They stuck to the moon's familiar face, the side permanently turned toward Earth. That changed on January 3, 2019, when China's Chang'e 4 spacecraft touched down in the unexplored vastness of the far side, a region hidden from direct view by the moon's own bulk. This wasn't just a landing, it was a technological high-wire act requiring solutions to a problem as old as spaceflight itself. How do you communicate when your target is shrouded in permanent radio silence? The moon's far side isn't merely unexplored, it's acoustically isolated. Earth's radio chatter can't pierce the moon's rocky bulk, making direct communication impossible. To bridge this gap, China launched Queqiao, a relay satellite parked 65,000 kilometers beyond the moon at Lagrange Point 2, a gravitational sweet spot where it can bounce signals between Earth and Chang'e 4 like a cosmic switchboard. This delicate ballet of orbital mechanics allowed the lander and its rover, Yutu-2, to transmit data through Queqiao while shielded from Earth's radio noise, an ideal setup for radio astronomy. Chang'e 4's landing site, Von Karman crater within the South Pole Aitken Basin, holds secrets older than life itself. This impact scar, over 2,000 kilometers wide and 13 kilometers deep, exposes the moon's primordial mantle, offering a window into the solar system's violent youth. Early findings shocked scientists. The rover's ground-penetrating radar revealed a subsurface layer of surprisingly porous material, suggesting a history of brutal impacts that shattered the lunar crust into a fractured sponge. But the real surprise came from the lander's mini-biosphere experiment. Cotton seeds briefly sprouted in the moon's weak gravity, marking humanity's first attempt at extraterrestrial agriculture. The mission's most groundbreaking achievement, though, was turning radio silence into an advantage. Shielded from Earth's cacophony of broadcasts, Chang'e 4's low-frequency radio spectrometer began probing the cosmic dark ages, the mysterious epoch before the first stars ignited. These faint signals, drowned out on Earth by FM static and Wi-Fi, could reveal how the universe transitioned from a featureless void to a tapestry of galaxies. Future far-side telescopes might detect whispers from the universe's infancy, clues to dark matter's nature or the first black hole's formation. Chang'e 4's success rewrote the rules of deep space exploration. Proving stable communication without direct line of sight opens doors for missions to Jupiter's icy moons or the solar system's uncharted reaches. More profoundly, it showcased the far side not as a dead zone, but as a pristine scientific haven, a silent sanctuary where the universe's oldest signals echo undisturbed. As Yutu-2 continues its lonely trek across the gray wastes, each wheel turn reminds us that the greatest discoveries often lie just beyond the limits of what we can see. The year 2020 marked a turning point not just in lunar exploration, but in how humanity might govern its celestial future, as nations and private companies set their sights on the moon's untapped resources. From water ice buried in polar craters to helium-3 ripe for fusion energy, the risk of territorial disputes loomed larger than ever. Enter the Artemis Accords, a daring diplomatic framework spearheaded by NASA to prevent the cosmos from becoming a new Wild West. At its core lies a revolutionary concept: safety zones, temporary buffers around lunar operations where conflicting activities would be prohibited. Picture two research stations mining the same ice field, or a rover accidentally damaging another nation's habitat. These zones aim to prevent such clashes by creating breathing room, much like maritime laws establish neutral waters around ships at sea. But the Accords go further, embedding principles of transparency and interoperability. Signatories, including the United States, Japan, and the United Arab Emirates, agree to openly share scientific data and adopt compatible docking systems, ensuring stranded astronauts could find refuge in any nation's habitat. The pact even addresses the thorny issue of resource extraction, permitting commercial use so long as it aligns with the Outer Space Treaty's ban on national sovereignty claims. This delicate balance tries to thread the needle between encouraging investment and preventing unchecked exploitation. Critics argue the Accords lack enforcement teeth, relying on goodwill rather than legal penalties. China and Russia notably abstained, labeling them a US-centric power play, while some scholars warn safety zones could morph into de facto territorial control if abused. Yet supporters counter that the alternative, a free-for-all scramble for lunar real estate, could trigger conflicts with consequences echoing back to Earth. Already, the Accords have reshaped missions like Japan's planned cargo landings near NASA Artemis Base Camp, where overlapping safety zones will require meticulous coordination. The true test may come when lunar water, vital for life support and rocket fuel, sparks competition. If one nation's safety zone blocks others from a prime ice deposit, tensions could flare. But if the Accords succeed, they'll set a precedent for governing Mars and beyond, proving humanity can explore without repeating Earth's history of conquest. The Moon is no longer just a destination, it's becoming a proving ground for whether we can cooperate in the cosmos as neighbors, not rivals. On July 12, 2022, humanity's most powerful time machine opened its golden eye, and the universe unveiled its secrets in colors no human had ever seen. The James Webb Space Telescope's first images weren't just photographs, they were cosmic love letters, each pixel a revelation stretching back billions of years. Among them, one image stole the collective breath of astronomers worldwide. The Carina Nebula's towering cliffs of gas and dust, glowing like a celestial cathedral drenched in starlight. But these weren't mere clouds, they were stellar nurseries where newborn stars sculpted their surroundings with hurricane-force winds, carving caverns of raw creation. Webb's infrared vision pierced through veils of cosmic dust that had hidden these processes from Hubble, revealing hundreds of previously invisible infant suns, some still cocooned in the very material that birthed them. Then came the real shock, galaxies that shouldn't exist. Webb's Deep Field snapshot of SMACS 0723, a galaxy cluster acting as a gravitational lens, exposed thousands of background galaxies warped into shimmering arcs. But the most distant among them, their light stretched into deep red by the expansion of the universe, appeared far too mature for their age. These galaxies, dating back to just 300 million years after the Big Bang, displayed structures as complex as modern spirals, contradicting theories that the early universe only hosted messy, chaotic protogalaxies. Their sheer brightness suggested rapid star formation, forcing cosmologists to reconsider how quickly matter clumped together in the cosmic dawn. Some even whispered the unthinkable: could our models of the early universe be missing entire chapters? Yet Webb's true magic lay in the details hidden within its spectra. When astronomers analyzed light from exoplanet WASP 96b's atmosphere, the data revealed the unmistakable fingerprint of water vapor, a first for a telescope not primarily designed as a planet hunter. This wasn't just about finding molecules, it proved Webb could detect the atmospheric composition of worlds hundreds of light years away, a critical step toward identifying potential biosignatures. Meanwhile, studies of the Southern Ring Nebula exposed intricate chemical fireworks, dying stars seeding the cosmos with carbon, oxygen, and complex organic molecules that might one day become part of new planets or even life. What makes Webb revolutionary isn't just its 6.5-meter gold-coated mirror or its cryogenic temperatures near absolute zero. It's the way this telescope straddles cosmic scales, zooming from the granular chemistry of planetary atmospheres to the vast architecture of the earliest galaxies. Every image is a Russian nesting doll of discovery, each layer peeling back to reveal deeper questions, older light, and glimpses of a universe far stranger than we imagined. We didn't just get a new window into space, we gained an entirely new set of eyes, capable of seeing the invisible and decoding whispers from the edge of time itself. For millions of years, Earth has existed at the mercy of cosmic chance, a spinning blue target in an asteroid shooting gallery. That changed on September 26, 2022, when humanity struck back. NASA's Double Asteroid Redirection Test, or DART, wasn't just another space mission. It was our first attempt to wrest control of our planetary destiny by physically altering the path of a celestial object. The target, Dimorphos, a 160-meter moonlet orbiting the larger asteroid Didymos, chosen because its predictable orbit posed zero threat to Earth, making it the perfect cosmic punching bag for this high-stakes experiment. The spacecraft itself was deceptively simple, a refrigerator-sized box with solar panels, carrying just one instrument, a high-resolution camera called Draco for navigation. But its real weapon was mass hurtling toward Dimorphos at 22,000 kilometers per hour. DART transformed itself into a 600-kilogram kinetic impactor, a high-speed bullet designed to transfer enough momentum to measurably shift the asteroid's orbit. Engineers held their breath as the probe approached its target, autonomous navigation algorithms adjusting its course in real time to zero in on the tiny, irregularly shaped rock. The final images streamed back to Earth in heart-stopping succession, Dimorphos' craggy surface filling the frame, boulders the size of houses looming into view before the signal abruptly cut off. Impact, then came the wait. Telescopes across Earth swiveled toward Didymos, measuring the telltale flicker of its light as Dimorphos passed in front. 2 weeks later, the results stunned even the most optimistic scientists. DART kamikaze strike had shortened Dimorphos' orbit by 32 minutes, far exceeding the minimum benchmark of just 73 seconds needed to declare success. The impact ejected thousands of tons of debris, creating a comet-like tail that stretched for 10,000 kilometers, adding an extra push through recoil. This wasn't just a nudge, it was proof that given enough lead time, humanity could deflect a genuine threat. The implications ripple far beyond this one test. DART revealed asteroids behave differently than lab models predicted. Dimorphos' rubble pile structure absorbed and redistributed energy in unexpected ways, crucial data for designing future deflection missions. Already, follow-up projects like the European Space Agency's Hera probe are en route to study the crater and measure Dimorphos' precise mass change. Meanwhile, NASA's NEO Surveyor Space Telescope, launching in 2028, will scan for potential threats years before they approach. What makes DART revolutionary isn't just the technology, it's the shift in mindset. For the first time in Earth's history, a species has looked at the stars not just with wonder, but with the capability to defend its home. The dinosaurs never saw their asteroid coming. Thanks to DART, we might not just see ours, we could stop it. Deep beneath the granite ridges of Lawrence Livermore National Laboratory, scientists achieved what was once considered impossible. A tiny capsule of hydrogen, smaller than a peppercorn, erupted with more energy than the laser beams used to ignite it. On December 5, 2022, the National Ignition Facility's monumental fusion experiment didn't just produce heat, it crossed the threshold of ignition, generating 3.15 megajoules of energy from 2.05 megajoules of input. For a fraction of a second, humanity replicated the fiery heart of the sun right here on Earth. The implications ripple far beyond the lab. Fusion, the process that lights the stars, could revolutionize space travel in ways chemical rockets never could. Imagine an engine where the fuel isn't cumbersome liquid hydrogen or toxic hydrazine, but isotopes of hydrogen extracted from seawater. Unlike today's rockets, which guzzle fuel just to escape Earth's gravity, a fusion-powered starship could accelerate continuously, reaching speeds that shrink interstellar voyages from millennia to decades. The math is tantalizing. A 1% light-speed vessel could reach Alpha Centauri in under 400 years, but with advanced fusion propulsion that drops to a single human lifetime. The NIF breakthrough offers a glimpse of that future. Their inertial confinement approach crushing fuel pellets with 192 lasers isn't practical for spacecraft yet. But spin-off technologies are already emerging. Compact laser arrays once the size of football stadiums now fit inside shipping containers, while advanced superconducting magnets could someday confine fusion plasma in portable reactors. Private ventures like Helion and Commonwealth Fusion Systems are racing to miniaturize these systems, aiming for reactor cores small enough to fit inside a starship's engine nacelles. Here's where it gets interstellar. Fusion engines wouldn't just offer speed, they'd provide unprecedented endurance. Current probes like Voyager rely on decaying plutonium batteries, their power fading after decades. A fusion drive could sustain itself for centuries, enabling missions that explore multiple star systems in a single launch. Picture a spacecraft that doesn't just fly past Pluto, but breaks into orbit around a planet in another solar system, deploying probes before refueling from cometary ice and racing toward the next destination. The challenges remain staggering. NIF's success required a building-sized apparatus to produce net energy for nanoseconds, while Starship engines would need compact, self-sustaining reactors firing continuously for years. Yet history shows once ignition is proven, engineering follows. The first nuclear fission reactor in 1942 led to nuclear submarines within 15 years. If fusion follows a similar trajectory, the first prototype Starship engines could be tested in orbit within our lifetimes. This breakthrough doesn't just promise cleaner energy on Earth, it opens a backdoor to the stars. The same physics that powers our sun might one day power vessels carrying human explorers to worlds orbiting other suns. We've taken the first step toward turning science fiction into flight plans. The universe, it seems, has left the ignition on for us. Imagine a spacecraft dipping through the icy geysers erupting from Enceladus, Saturn's snow globe moon, its instruments suddenly blinking with the unmistakable chemical signature of organic molecules arranged in patterns only life could produce. Or picture a high-altitude probe floating in Venus's sulfuric acid clouds, detecting not just trace amounts of phosphine, a gas often associated with microbial activity on Earth, but entire colonies of extremophile organisms thriving in an environment that would dissolve a spacecraft in hours. These aren't just scenarios ripped from science fiction, they're real possibilities that astrobiologists are actively preparing for, and if proven, they would shatter humanity's oldest existential question: are we alone in the universe? Let's start with Enceladus, a small, frozen moon that hides a vast liquid ocean beneath its icy shell. What makes this world so tantalizing isn't just the presence of water. It's the way this moon actively sprays its subsurface ocean into space through massive cracks near its south pole. NASA Cassini spacecraft already detected hydrogen, carbon dioxide, and even complex organic molecules in these plumes, hinting at hydrothermal vents on the seafloor below, environments strikingly similar to those where life thrives in Earth's deepest oceans. Future missions, like the proposed Enceladus Life Finder, could analyze these plumes for amino acids or, more provocatively, lipids and proteins. Finding either would be like stumbling upon a floating restaurant in the middle of the desert, evidence that somewhere beneath that ice, chemistry has crossed the threshold into biology. The implications would ripple far beyond science. For the first time, we'd know life isn't a fluke. It's a cosmic inevitability, sparking wherever conditions allow. Then there's Venus, Earth's twisted sister, a hellscape with surface temperatures hot enough to melt lead and pressures that crush submarines. Yet high in its atmosphere, in a temperate layer of clouds 50 kilometers up, scientists detected phosphine in 2020, a gas that on Earth is predominantly produced by anaerobic bacteria. The discovery ignited fierce debate. Some argued volcanic activity or unknown chemistry could explain it, while others pointed out that no known abiotic process generates phosphine in such quantities. Imagine a follow-up mission like the privately funded Rocket Lab probe slated for the mid-2020s, not only confirming phosphine but capturing images of microscopic, sulfur-resistant microbes drifting through the Venusian haze. Suddenly, life isn't confined to Goldilocks zones. It's tougher, weirder, and more adaptable than we dreamed. The philosophical aftershocks would be profound. If life exists in our solar system's harshest corners, then the galaxy could be teeming with it. But more startling is the possibility that we might find life, yet never recognize it as such. Silicon-based organisms, self-replicating crystals, plasma entities in Jupiter's magnetosphere. The discovery of alien microbes wouldn't just answer one question. It would unleash 1,000 more, forcing us to redefine life itself. And if that life shares our biochemistry using DNA, proteins, or even the same amino acids, it could hint at something even more staggering, that we're all part of a cosmic family, seeded across worlds by comets or some ancient interstellar diaspora. Either way, the moment we confirm extraterrestrial life, humanity's story changes forever. No longer isolated, no longer accidental, we become part of a living, breathing cosmos. And that revelation wouldn't just belong to scientists. It would rewrite our myths, our art, even our religions. The universe, once silent, would finally whisper back. The moment we've imagined for generations is finally on the horizon, boots crunching into the rust-colored dust of Mars. By the 2030s, SpaceX's Starship or NASA Artemis-derived deep space vehicles could launch the first crewed mission to the Red Planet, marking humanity's evolution into an interplanetary species. But reaching Mars isn't just about strapping astronauts to a rocket and pointing it toward the fourth planet. The challenges are so immense they make the moon landings look like a weekend road trip. Take radiation, the silent killer lurking between worlds. Unlike Earth, which shields us with its magnetic field and atmosphere, Mars offers little protection from cosmic rays and solar storms. A round-trip mission could expose astronauts to radiation levels exceeding lifetime safety limits, increasing cancer risks and potentially damaging brain tissue. NASA's solution: layers. Starship's stainless steel hull might be lined with water-filled compartments or even lightweight polyethylene, rich in hydrogen atoms to deflect particles. Some propose active shielding artificial magnetic fields enveloping the ship like an invisible force field. But no system is perfect. Astronauts may need to huddle in storm shelters during solar flares, surrounded by food packages acting as makeshift radiation buffers. Then there's the 9-month voyage itself, a psychological marathon in a tin can. Unlike Apollo astronauts who saw Earth throughout their journey, Mars-bound crews will watch their home planet shrink to a pale blue dot within weeks, confronting total isolation. To combat the mental toll, SpaceX envisions Starship's spacious interior with private cabins, communal areas, and even large screen displays simulating Earth's daylight cycles. But no amount of VR can replace real sunlight. NASA studies on the International Space Station show long-duration crews face sleep disorders, irritability, and declining morale. Add the knowledge that rescue is impossible, Mars is simply too far, and every crew selection becomes a high-stakes gamble on human resilience. Landing on Mars presents its own nightmare. The planet's thin atmosphere offers just enough drag to make entry dangerous, but not enough to slow a spacecraft gently. Starship's proposed solution is a belly flop maneuver. free-falling through the Martian sky before flipping upright and igniting engines for a pinpoint touchdown. One miscalculation and the ship could tumble, crash, or run out of fuel mid-flip. NASA alternative, using advanced parachutes and retro-rockets, isn't any simpler. Mars's unpredictable winds have wrecked more than one lander. Survival on Mars hinges on what's called in situ resource utilization, living off the land. Water ice mined from the soil could be split into oxygen for breathing and hydrogen for fuel. The carbon dioxide-rich atmosphere might feed algae farms or be converted into methane for return trips, but these technologies remain untested at scale. A single malfunction in the life support system, say a clogged CO2 scrubber, could turn the habitat into a death trap. Backup systems upon backup systems will be essential, alongside 3D printers capable of fabricating spare parts from Martian dust. Perhaps the most haunting question isn't technical but ethical. If something goes wrong, if a crew is stranded or dying, do we attempt a risky rescue or accept their sacrifice as the price of progress? The first Martians won't just be explorers. They'll be pioneers in a wilderness with no precedent, where every sunrise is a hard-won victory over an indifferent cosmos. Yet for all the risks, the reward is unparalleled proof that we're not tied to one world, that even in the face of lethal radiation, bone-cracking landings, and crushing isolation, humanity can plant its flag on another planet and call it home. High above the Earth's atmosphere, where sunlight never dims and clouds never form, a fleet of colossal structures unfolds like futuristic origami, each kilometer-wide array capturing the pure, unfiltered energy of the sun 24 hours a day. This isn't science fiction. It's the bold vision of space-based solar power, a concept poised to revolutionize how humanity fuels its future. Imagine solar farms in geostationary orbit, converting sunlight into microwave or laser beams, transmitting gigawatts of clean energy down to receiving stations on Earth with pinpoint accuracy. Unlike ground-based solar panels shackled by nightfall and weather, these orbital power plants could deliver a constant, uninterrupted flow of electricity, rain or shine, day or night. The implications are staggering. If perfected, this technology could single-handedly displace coal and gas plants, slashing global carbon emissions while meeting skyrocketing energy demand. The physics behind it is deceptively simple. Sunlight in space is up to 11 times more intense than on Earth's surface, with none of the atmospheric scattering that saps efficiency. Modern photovoltaics can already convert over 40% of that light into electricity, far better than terrestrial panels. The real challenge lies in beaming that energy across 36,000 kilometers of void. Engineers have tested microwave transmission since the 1970s, using phased array antennas to focus energy into tight beams, harmless to anything outside their ground-based receiver, a technology likened to catching sunlight with a butterfly net. Recent breakthroughs in wireless power transfer at agencies like JAXA and Caltech prove it's possible. In 2023, researchers successfully transmitted solar energy from orbit to Earth for the first time, converting microwaves into usable electricity with no moving parts. Yet the hurdles are as vast as the potential. Constructing kilometer-scale solar arrays in orbit demands robotic assembly or in space manufacturing, leveraging technologies like SpaceX's Starship to slash launch costs. Each station could weigh thousands of tons, far heavier than the International Space Station, requiring advances in lightweight, self-repairing materials. Then there's the energy loss during transmission. Even with 90% efficiency, a fraction of that power dissipates as heat in the atmosphere. Critics argue that ground-based renewables paired with grid-scale batteries might outcompete orbital solutions economically, but proponents counter that space solar's unique advantage is scale. A single array could power a mid-sized city, and a constellation of them could meet the baseline needs of entire nations without consuming a single acre of land. The geopolitical ramifications are equally profound. Nations mastering this technology would wield unparalleled energy independence, no more oil wars or pipeline disputes, just an equitable cosmic energy grid. Early adopters like China and the UK have already drawn up roadmaps with pilot projects slated for the 2030s. Private ventures, including startups like Solarin and Space Solar, are racing to deploy demonstrator satellites, betting that the economics will tip in their favor as launch costs plummet. The ultimate goal, a network of orbital power stations feeding a global clean energy web, turning every desert, tundra, or ocean into a potential receiver site. Beyond Earth, space-based solar could be the key to thriving off-world colonies. Mars settlers, for instance, might rely on orbital mirrors or solar satellites to compensate for the red planet's weaker sunlight, enabling large-scale agriculture in domed habitats. Lunar outposts could beam power to shadowed craters where water ice hides, eliminating the need for dangerous nuclear generators. If perfected, this technology wouldn't just solve Earth's energy crisis, it would become the backbone of interplanetary civilization. What makes space-based solar power so tantalizing isn't just the promise of clean energy, it's the audacity of harnessing the cosmos itself to heal our planet. Unlike fusion, which remains decades away, or carbon capture, which treats symptoms rather than causes, orbital solar arrays offer a near-term solution using existing physics. The obstacles are immense, but so were those facing the Apollo program or the Large Hadron Collider, and humanity prevailed. If we succeed, future generations may look back at coal stacks and oil derricks as relics of a darker age, marveling that we ever powered our world by scraping the ground when the infinite energy of the stars was just overhead, waiting to be tapped. Picture this, a wafer-thin sail, no larger than a picnic blanket yet stretching kilometers wide when unfurled, catching the momentum of 1,000,000 laser beams fired from Earth's orbit. In the 2070s, humanity could launch its first intentional messenger to the stars, an interstellar probe bound for Proxima Centauri b, the closest known exoplanet that might harbor conditions for life. Unlike traditional rockets weighed down by fuel, this spacecraft would harness the pressure of light itself, riding laser-pushed photon momentum to velocities previously reserved for sci-fi, up to 20% the speed of light. At that pace, the 40 trillion kilometers to our nearest stellar neighbor could be traversed in mere decades rather than millennia. The technology, surprisingly, isn't pure fantasy. Breakthrough Starshot, an initiative backed by luminaries like Stephen Hawking and funded by Silicon Valley visionaries, has already demonstrated prototypes of these light sails constructed from ultra-thin metamaterials stronger than steel yet lighter than air. When a ground-based array of gigawatt lasers, synchronized like a cosmic symphony, strikes the sail's reflective surface, the resulting acceleration could propel a gram-scale payload to relativistic speeds in minutes. That payload, a fleet of nanocrafts, each no heavier than a paperclip but packed with sensors, cameras, and even rudimentary AI to analyze Proxima b's atmosphere, oceans, or even artificial structures should they exist. But the real magic lies in the sail's design. Engineered to withstand the brutal onslaught of interstellar dust impacting at a fraction of light speed with the force of nuclear collisions, its surface would self-heal using microscopic fluid channels akin to biological cells. Meanwhile, onboard communications would rely on an equally ingenious solution: a 1-watt laser beacon, faint as a candle flame by the time it reaches Earth, requiring kilometer-scale telescope arrays to detect its whispers across the light years. This mission wouldn't just be about exploration, it would be a time capsule of human legacy. Etched onto the probe's nanostructures could be the sum of our knowledge, from DNA sequences to digitized art, a backup of civilization in case of terrestrial catastrophe. There's poetic symmetry here. Just as ancient mariners launched messages in bottles into unknown seas, we'd cast our technological equivalent into the cosmic ocean, unsure if or when it might find a shore. Yet the challenges are as staggering as the ambitions. Maintaining laser focus over interstellar distances would demand precision beyond anything engineered before. A single misaligned mirror could scatter the beam into uselessness. Then there's the chilling reality of one-way travel. Even if the probe survives the journey, its data would take over 4 years to crawl back to Earth at light speed. And lurking in the void are hazards no blueprint can fully anticipate: cosmic rays degrading electronics, unforeseen gravitational tugs, even the remote possibility of encountering alien debris fields. What makes this endeavor revolutionary isn't just the engineering, it's the shift in mindset. For millennia, stars were untouchable jewels in the night. Now we're not just dreaming of reaching them, we're plotting the logistics. A successful launch would prove that interstellar travel isn't bound by the limits of chemistry or rocket equations, but by our ability to harness fundamental physics on a grand scale. More than that, it would signal to the universe and to ourselves that we're ready to step beyond the cradle, not as conquerors, but as curious neighbors knocking gently on the galaxy's door. The probe's voyage would unfold on timescales longer than most human careers. Those who launch it may never see its destination, but their children or grandchildren might. In that act, planning for a future we won't live to witness, we demonstrate something perhaps even rarer than advanced technology: the audacious patience required to truly become an interstellar species. The stars have waited billions of years for visitors. Thanks to light sails and relentless curiosity, our reply is finally en route. From the unimaginable violence of the Big Bang to the delicate whispers of gravitational waves, these 30 cosmic events aren't just milestones, they're the turning points that shaped and will continue to redefine our place in the universe. Each one is a thread in the grand tapestry of existence, from the chance collision that gave us the Moon to the stubborn Mars rovers uncovering the ghosts of ancient rivers. Think about it, without that primordial asteroid bombardment, Earth might never have gained its oceans. Without Galileo's telescope, we'd still see ourselves as the center of creation. And without the audacity of DART asteroid deflection test, we might have remained sitting ducks in a cosmic shooting gallery. The beauty of these events lies in their duality. They're both accidents and inevitabilities. Theia's catastrophic impact with Earth was a fluke of orbital mechanics, yet it set the stage for seasons and tides that nurture life. Hubble's flawed mirror felt like a failure until its repair unveiled the glow of galaxies born near the dawn of time. Even now, as private companies like SpaceX make rocket landings routine, we're witnessing what happens when stubborn curiosity meets relentless innovation. This isn't just progress, it's evolution with purpose, a testament to life's drive to reach beyond its cradle. Looking ahead, the next chapters are ours to write. Will we be the generation that discovers microbial life swimming in Enceladus' hidden sea, that plants crops in Martian soil, that unlocks fusion propulsion to sail the stars? The cosmos doesn't hand out guarantees, only opportunities. Those shimmering exoplanets Webb found, those mysterious fast radio bursts from distant galaxies, even the unsettling Oumuamua zipping through our solar system, they're all cosmic breadcrumbs, hints that the universe is far stranger and richer than we've dared to imagine. So stay curious. The next civilization-altering discovery might come from a teenager analyzing telescope data online, or a robot cracking open a meteorite on Titan. Space isn't just a destination, it's a conversation, an infinite puzzle inviting us to ask, what's next? Whether you're gazing at the night sky or brainstorming the next breakthrough, remember, every revolution starts with someone refusing to accept that the unknown must stay that way. The stars aren't just points of light, they're waypoints on a journey we've only just begun. And if history has shown us anything, it's that when humanity dreams big enough, even the impossible becomes just another item on the to-do